Alright, here is everything you need to know about Big Idea 5. We're starting with chemical reactions. In a chemical change, we're going to break and make bonds. So let's start with something kind of classic, C3H8. It's a hydrocarbon plus oxygen. A combustion reaction that's going to make CO2 plus H2O. We'll have to balance the equation, of course. 6, 6, and 9. Now, in a chemical equation, what we're really focusing on this chapter is this change in H over here. It's some sort of number. And that number is going to have units of kilojoules per mole of reaction. Now, that's really specific. We've talked about a lot of terms of this, but this is called the heat of the reaction. That's a generic way to call it, but since we know this is a combustion reaction, I know it's combustion because there's oxygen in here, and oxygen is going to make a boom. Boom. So if I wanted to call it differently, I could call it the heat of combustion. These heat of somethings is just really telling you more specifically what kind of reaction it is. You could just be generic and call it reaction, or you could be more specific and call it combustion reaction, heat of combustion. Now things change a little bit because this isn't the molar heat of combustion. Molar heat of combustion is different. A molar heat of combustion suggests you have 1 mole. That's what molar means, which means if you look over here, the reaction really has 2 moles. So the molar heat of combustion is going to be that number divided by 2 in this case, because that's the number of moles that I'm combusting. This heat of reaction can be calculated in a couple different ways. So how can we find the heat of the reaction? Number 1, let's try calorimetry. Calorimetry is where you find Q, and you get that by doing Q equals mc delta T. And then sometimes, if you're lucky, you could use the calorimeter constant right here. But a lot of times you're not going to use it. Sad face. That stinks. Calorimetry is when you're using that styrofoam cup or the calorimeter that's in the styrofoam, and you have a thermometer inside, and you're really taking the change in temperature. Remember, temperature is not the same as heat. Temperature and heat are related by heat being the flow of energy due to a temperature difference. So we can use this change in temperature to find the heat. Going to number 2, we can find this heat of reaction in another way. We'll use the heat of formations. The heat of formation is when you're finding the heat of the reaction using summation of the products minus the summation of the reactants. It's an equation that's on your equation sheet. Another way we can do this is to use the break minus the make. That's using bond energies, or more specifically bond enthalpies. Remember, H is enthalpy. So going back over here, these are the ones that you break, and these are the ones that you make. So we have to draw the Lewis-Dot structure to figure out what we've got. CO2, H2O, O2, let's put some I's on there in happy case, CH3, this one actually happens to have a double bond, C3H, this should be 6, sorry, we've got hydrogen around the outside that we don't have, 1, 2, 3, 4, 5, 6, those are my hydrogens. So if you wanted to decide break minus the make, you'd have to count how many bonds you have, 1, 2, 3, 4, 5, 6 CHs. You got a double bond C and a single bond C, and you're going to add up all the ones that you break. Don't forget that this is 9 times that, 9 oxygens, and this is 2 times that. Minus the make, 6 CO2s and 6 waters. Break minus the make will bring you back down to our bond enthalpy. Number 4 way to find our heat of the reaction is to use Hess's law. Hess's law, if you have to have different equations adding up, like A plus B makes C, and C plus D makes E, and C and E could cancel off, and we can make A plus B plus D to equal E. And if you add up all those H's, sometimes you might need to flip them, you can actually get the heat of the reaction. Okay. Let's zoom this out. Those are the 4 different ways that I can actually find the heat of the reaction. But if you think about it a little bit differently, this heat of the reaction is really telling us a lot of good things. This is a combustion reaction, so it's going to be negative. If the heat of the reaction is negative, we've got an exothermic reaction. If it's positive, we've got an endothermic. In this case, we have combustion, so it's got to be exothermic, which means if we take a look at the reaction coordinate diagram, we've got the reactants, break, and make, and here's my products here. This is your potential energy, and this is your progress over time. Here's your activation energy. Here's your change in H of the reaction, which is this number. Bring it a little bit further back. Remember, this is the break. Breaking is what happens here on the uphill. Minus the make. Makes what's happening on the downhill. And those two together, if you do the break minus the make, you're going to get the heat of the reaction. Man, I sure wish I was sledding right now. Whee! But then you always have to walk back up the hill. Oh, so sweet. But the sledding is totally worth it. Okay. We got to move on to a different side. Let's move over here. Zoom it out. We've got physical changes. Physical changes are really kind of the same thing, but now we've got to think of the woot-woot curve. Woot, 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 woot. Remember this? This is your temperature. This is the heat input. We've got solids, liquids, gases. We've got our phase changes in between. And here we've got to look at our equations. Q equals N delta H. Remember, this one's kind of tricky because N could be moles or grams. It kind of depends what H is in, so be careful. But this H is really heat of something. Are you doing fusion? Fusion is going from a solid to liquid. That's going on down here. Are you doing vaporization? That's going on up here, vaporization. It's all really the same thing because it comes down to an equation, like with water. If we have water as a solid, making water as a liquid, it's really just the heat of something for the heat of the reaction. In this case, it just has a special name. In this case, it's heat of fusion. Same thing as a chemical change. You're just getting lots of H's. And you can find that any different way, too. Think about our chemical change and the 4 ways to do it. You could do the same thing here. It's all the same. Let's zoom out. These 4 ways of finding the heats of a reaction and a chemical change could really be listed over here, too, as the heat of whatever you want to find. They're all the same sort of deal. Moving back over to this part, as a reminder, these are the temperatures, your boiling point, your freezing point, temperatures at which things change their intermolecular forces, because we're looking at physical changes here. The higher the boiling point, that means the stronger the IMFs you've got going on. Man, let's go up this hill. Seconds. If you take these two parts and we think about them together, we can actually apply our last part. Change in G equals change in H minus T change in S. Once again, we're looking at H. That's most of the chapter is talking about H. H is enthalpy, that's looking at heat. That's our endo or exo. But G is our Gibbs free energy. If that's negative, then it's going to be thermodynamically favorable. The cheater way of thinking about it is spontaneous. If it's positive, that means it's not spontaneous. Or it's not thermodynamically favorable. We can find these sort of things by using the equation that's on the equation sheet. It really looks the same as the other one we were doing. Products minus summation of the reactants. Same thing. If we move over here to S, S is entropy. And we can use that same reaction for entropy. If you wanted to find the entropy change for a reaction, again, you're going to use the summation of the products of their S values, or entropy values, minus the summation of our reactants, products minus reactants. And in the end, you're going to get a number. If it's a positive S, well then, that's different from a negative S. A negative S means that things are going to be more ordered. And a positive S, that means it's crazy, it's chaos. Is that how you spell chaos? I'm not sure. Not sure. Sorry. I think that ends my story. Man, here's me. I'm feeling pretty awesome. I'm gonna high five other me on the chemical side. Hey me, you did a great job.